Hello and welcome to another session of SOYO STEM on Your Own. This is session 4 of the Basic Electrical Theory course that I'm going through. This one is going to be solely on Kirchoff's voltage and current laws. There's two of them. I've mentioned them in two of the previous videos, and perhaps all three. But I don't think that I've spent enough time on them. These are extremely fundamental, and if you do not understand them, please leave a comment or email me, and we'll try to get your questions answered. This is absolutely fundamental for anything in circuit theory. That's just kind of the way it is. So if you don't understand it, it will cause serious issues. So we're going to try to do it a little bit more detail and going to use one particular example. It's a little bit more complicated, but I'm trying to do it so that we can see everything tied together instead of just looking at one portion at a time. I think it should help solidify things. So let's just jump right in. So we've got to define them again. So the KVL, which is Kirchhoff's voltage law, states that the sum of the voltages around any closed loop, oops, if I could write, equals 0. So, and we'll just go into the KCL as well. And then the sum of the currents at any one node equals 0 as well. So the best way to talk about this, so a loop is anything, or we'll just talk about this with the example. So I've written it out ahead of time so that we're not wasting a whole bunch of time watching me do my horrible drawings. This took a lot longer than I would like to admit. But regardless, we'll just look at this one example. That should be all we need. Actually, I'm going to move this more to the center so we have more room to play around if need be. All right, so we've got this more complicated circuit than anything else that we've dealt with so far or anything that I've brought out. So we can see several loops here. So we'll just look at the KVL and then the KCL. So loop here, this loop will here, oops, if I could draw an arrow. All right, pardon my horrible, well, I'm just going to fix that. This is loop 1, we'll call that. We'll call this loop 2. This we'll call loop 3. So we have loops 1, 2, and 3. What we can do, and this is something that I will discuss in a later video, so I'm going to simplify this circuit real quick. Just to kind of, there's a point that I'd like to try to illustrate, and I can't do that with the current configuration. Alright, so this is R1. This is R2 parallel with, parallel with R3. This is R4, R5, R5, not 5, and R6. So this here, this is a simplification that we can make, and I'll be talking about that in a later video. But that being said, so this would be our loop 1. This again would be our loop 2. So these are the same loops as before, except loop 2 is now with R2 parallel with R3 resistor. And then we also have a third loop in this particular circuit as well. We can go all the way around here, and that could be our loop 3. Well, it would technically be loop 4. And the reason we could not do that before is because we had this section up here. This section would cause us to not be able to do that in the first circuit that we drew. So let me just get rid of this real quick. I'll just cut that out. All right, so let's go back to this main thing. So the sum of any voltages around any closed loop equals 0. So if you only have 2 elements in a loop, so like loop 3 is the only one with only 2 elements in the circuit, you'll find that those are parallel, and that's just kind of the way things go. So if we'll just do voltages to begin with, and then we'll go through and do the nodes and the currents. Or actually, yeah, we'll do that. Okay, so if this, we'll call this V1, we'll call this, V5, and then we'll call this V6. Okay, hopefully that's clear. I'm going to make this slightly bigger. I can't make it any bigger, at least on the screen here, so I'm just going to circle that. Just make it bigger. All right. Hopefully that's clear. Anyways, so this would mean, and we'll call this Vs for V source. So by the KVL, the sum of the voltages around any closed loop equals 0. So that would mean, so as we're coming in this is a voltage rise. So Vs is going to be equal to let's set up exactly. So 0 equals Vs minus, because we're going in the plus on this side here. So minus V1, coming around loop 1 here. So we're coming around in this section here. Minus V5. And then same thing down here. We're coming in this way. So minus V6 is equal to 0. So this could be rewritten as Vs equals V1 plus V5 plus V6. And this will be true regardless of how the situation is. So if we want to go, so this is for loop 1. For loop 2, we'll do, so this would be V4. I'm just going to do all the voltages. V3, oops. V2, and it doesn't really matter which way that you orient your pluses and minuses on these. If it happens to be a negative voltage when you do all these equations over here, if let's say V6 is negative, what you would do is just switch these polarities. So this would be a plus, and then this would become a minus. As far as what the actual voltages are, but that's something that we'll discuss as we actually do problems at a later time. This, I'm just trying to get a general feel for how these things work. So starting here with loop 2, so if we start at R5, so we're coming up into the negative side, so that would be a voltage rise. So 0 equals V5. On V3, we're coming into the positive side, so that's a drop, minus V3. Then we're also coming into the positive side on R4, so it'd be minus V4. So this would also become V5 equals V3 plus V4. Oops, V4. And then looking at loop 3, we have, if we start at R3, So 0 equals negative V3, because we're coming in on this side if we're going around the direction that we're saying. And then we're coming in on the positive side on R2. Or I'm sorry, opposite way. So if you're coming in on the negative side, you're having a voltage rise. So that would be V3 minus V2. Because we're coming back all the way around here, and then we're getting that minus on that V2. So V3 equals V2, which checks out because these are parallel, which that's kind of the designator for the parallel, or that's a symbol for parallel elements. So V3 equals V2, which makes sense. As a caveat to all this, as far as this entire section goes, physics majors and just the physics community does the exact opposite of this. So if you're taking a physics class, they will tell you differently, but most of the electrical engineering community kind of ascribes to this. So if you're a physics person, just do it backwards. As far as if you're coming into the positive side, that would be a voltage rise. If you're a physics major, if you're coming in this way as a physics major, that's going to be a voltage rise. If you're coming in this way, that's going to be a voltage drop. That's just it doesn't really matter. You still get the same answer. Technically, just pluses and minuses are backwards. So it's not a big deal. Just be aware if you go into a physics class, they might tell you differently. But it's okay. So that's the KVL. And so now we're going to delete all this here. Now that we're back to our original circuit with minor cosmetic issues. Now let's talk about the KCL. So any one node, which technically means anything that has more than one wire attached to it. So this point here, this would not be considered a node. This point would be considered a node. This point would be considered a node. And this point would be considered a node. So if it has more than, let's say if we were going in this direction, if you consider that this is an input and these are outputs, as long as there's more than one output per input, that would be considered a node. Which is the technical definition. Really, it doesn't matter. If you wanted to consider, let's say that first point a node, if you wanted to consider that point a node, it would technically be accurate. It's just going to take you a lot longer to do the circuit analysis. So you're going to have a current coming this way, so we'll call this IS. And you're going to have a current coming out. That's also going to equal IS. So you have an input of IS, and you have an output of IS on that, and that's going to equal 0. Just they're the same current, so they're going to equal 0. So it's technically accurate as far as the KCL is concerned, but it is going to take you a lot longer if you doing circuit analysis if you decide to go through every single node, non-node like that. So really, the points that you want to look at, we'll call this point A. We're going to call this point B. We're going to call this point C. So that's what you want to look at. So this is going to be I1. It's going to be I2, I3, I5, I4, and then we'll do I3 and I2 on this as well. And then this is going to be I4, I5, and this is going to be I6. All right, so now that we've got this all set up, so if we're just considering and again, it doesn't really matter which direction that you assume. As you get better at this, you'll kind of pick up which direction you should assume, so that you get all positive numbers at the end, so you don't have to fix your diagram at the end, because it seems to be a pain in the butt later as far as messiness goes. But let's kind of go through this. If I can get this erased. All right, so let's look at node A. So what we have coming into the node, or let's just do this. So coming into the node is just I1. As you can see, I5, I3, and I2 are going out. So 0 equals I1 is the only positive, and then I2, I3, and I5 are all coming out. I2 minus I3 minus I5. So fairly straightforward on that one. So then I1 is equal to I2 plus I3 plus I5, which kind of makes sense if you think of conservation of energy, if you are familiar with that. If not, look it up on Wikipedia. It just means you can't get more energy than out than you put in. So you can't get more current than you put in if your voltage is staying the same. There are ways to do that, but that's only with alternating current. Not strictly true, but we can talk about that at a later time. It's a more advanced topic. So if we look at node B, we have 0 as well. It's always going to be 0 equals. So right now we see I2 and I3 are both of these are coming into node B. So if we do, so that's going to be I2 plus I3, and then we only have I4 coming out. And then so we subtract I4. And so I4 is equal to I2 plus I3. That's all there is to it. And then again, looking at C, we see I4 is coming in, 0 is equal to I4 minus plus I5, I'm sorry, because I5 is also coming in, minus I6. So then I6 is equal to I4 plus I5. So that's kind of the basics of everything. And, these are 3 different equations. We have a lot of unknowns. You can find some of those. So if you have a voltage, say, across R5 or something like that, so those voltage equations that we talked about in the first video, those would be helpful here. And that's how you would do circuit analysis. So I think the next video will actually do some circuit analysis, maybe even on the same circuit, and actually assign values and see what we get out at the end. So thank you again for watching. Again, if you have any questions, comments, concerns, please leave them down below. I will get them answered. I was having some issues with my notifications. I think I've got that fixed now. And I would like to just get you to understand this if you don't understand it. Anyways, thank you. Please leave a like, subscribe. If you think of anybody that might benefit from this, please send them a link to the videos, and I'll be happy to help them as well. Thank you, and have a good rest of your day.